or quadratic shape element, triangular element, right? And what we have, so you can see on the slide, we are going to discuss plasticity a little bit. We have discussed already. So one method is Newton-Raphson method for predicting what happens, in which you will be calculating for every increment of displacement, you have to calculate the stiffness matrix. Okay. So when we solve for a static problem, okay, so let me explain that. There is a movement in the tensile sample when you are stretching it. Okay, so there is a displacement. If the displacement changes with time, there is a velocity, and if that changes with time, you have acceleration. Okay, so that will be causing some force will come because of the inertia of the material, and then you have Newtonian forces because of acceleration. Okay, and we are not taking those into account in our solution. When we take displacement and we come to the solution, which is force is equal to the stiffness matrix into the displacement column matrix. In this case, we don't have acceleration, we don't have double differentiation of displacement or the first differentiation of the displacement. Okay, so these are static problems. Although there is a displacement in sample, we don't take motion into account. So that's why these are called static problems. And they are really not static, so they are called quasi-static. Okay? Quasi meaning not really, false static. Okay? So all the problems which you are trying to solve using this method, which we have explained, which we have discussed so far, are going to be very, very slow deformation processes. So all those deformations which will not show time dependence and which will not have inertia effect, which will not have very high strain rate, all those problems will be solved using this equation and the methods which we have discussed. If we have velocity and acceleration, so that means examples are where a bullet is hitting a target. Okay, so there you have inertia effect of the target, and you have Newtonian forces because of the acceleration of the bullet also. And in that case, the equation which is being solved will change, and you will have acceleration also. Okay, so you will have forces which will be coming because of the mass into acceleration. Okay, so you will have k into u transpose, which is coming because of this minus that should be equal to 0. Something like this you will have to solve. And these are called dynamic problems. Okay? And dynamic problems can be solved by two methods. If time permits, we will see those. So one is implicit and another is explicit. The solutions are updated at the end of the increment in implicit, and in explicit it happens in the beginning. That's the main difference. Okay, but we will discuss this if time permits. So for now we don't have accelerations and we are trying to solve quasi-static problems, and then once things go beyond elasticity, then we have to solve for plasticity. And for plasticity, the stiffness matrix will be taking the approximation of the slope from the initial point. At ith iteration, you will have an approximation of the slope at that point, and then you will try to hit another point, and from that point again you will calculate the tangent, and then you will find out the new stiffness matrix. That is Newton-Raphson. Okay. Modified Newton-Raphson is same thing, but you don't change the stiffness in every iteration, not every increment. In one increment you can have more n number of iterations for convergence. Okay. So plasticity in the material can be modeled using three types of ways. So what are those three types? So you can have ideal or perfect plasticity, which is simply this. Once it hits the yield strength, then nothing changes in the stress. Okay. The second thing is you can have isotropic hardening. So perfect plastic or ideal plastic, there is no hardening, there is no softening also. In isotropic hardening, you go to the first yield point, okay, and then if you further increase the strain, you will have an increment in the stress. And then when you unload, it will follow the same slope, and in the reverse direction, it will go to the same value of sigma E. It will go by the same amount of hardening, and then you will come back. Right? So this is sigma naught in tension, and this is sigma naught in compression. And it will be hitting the same value in tension and compression. That's why it is isotropic. Okay. The other case can be where it goes to a certain value of hardening, and then when you reverse the direction, then it really will not go to that value of yielding, but it will yield a little before, and then it will harden by whatever slope you are defining for the hardening, and it will come back. So in this case, this distance is always going to be constant. Okay. So from here to the first yield point and the second yield point to the second yield point, that distance is going to be constant, and it is always going to be 2 times of sigma naught in the yellow case. In the blue case, always this distance between the two yielding happening in the tension and compression is increasing every time. In the yellow case, that difference is not changing, that is constant. Okay. So you have an early yielding in the reverse direction. So that is called kinematic hardening. You have a back stress by which you subtract so that the total is 2 sigma naught. Okay. So the second case is valid for many metallic materials which show a Bausch-Singer effect. If you remember what that was. So when dislocations are moving, they are getting blocked at barriers like lower cortical, and they are getting blocked at the grain boundaries, and they are getting blocked at twin boundaries, precipitates, dispersions, or any secondary phase you have. When you reverse the direction of stress, then what happens? They are blocked, so dislocations are moving, and they have been divided, so not all of them, but the first one will be divided in 2 Shockley partials. Okay, so A0 by 6, 1 to 1 type of dislocation, and these two will they will create a geometry which will have a fault in stacking, and then they will get blocked here when the two planes are intersecting. Okay, both of these two planes are of 111 type and the directions are 110 type. This is the case for FCC and this is the lower partial barrier. Okay, so they will be getting blocked here and the shear stress is in this direction. Once you reverse the direction of loading, then these dislocations are not going to move in this direction, they are going to move in that direction, right? So their movement is not really blocked now, they are now open to move, so that's why they don't need that much amount of stress which you need to go in this direction. If you have a precipitate and the dislocation is blocked or piled up along this direction because your shear stress is such, if you reverse the direction, they are not locked, so they can move. Okay, so this is the reason for Plasticity effect, that when you reverse the direction, the yielding, the dislocation movement can happen at a lower stress value. Further strengthening also can happen at lower stress value. Okay, so this can be represented well by kinematic hardening, the second type of way by which you can model the hardening. Okay, so this would be ideal plastic condition. Okay, and then it goes on and on. In case of ideal plastic, this curve is going to be same. The strain will increase, but stress will not increase. Okay, so and then in isotropic, it is going to have the same distance in the tension direction and in the compression direction. Okay, so this is going to be same. So this is same, this is same, this is same, that is same. It is going to yield at exactly same value of yield strength, whether or not it is tension and compression. That is the meaning of isotropy. Okay. Well, isotropy or anisotropy is can be used in different different types of deformation differently. So this is plastic isotropy. Okay. Elastic isotropy is different. Elastic isotropy would mean that you have Young's modulus same in every direction. You can have situations like orthorhombic or monoclinic crystal structures where elastic modulus will be different in different direction. Also, there will be cases if you roll your material, you can have different elastic modulus in different direction. Also, you can have different yield strength in different directions. So, when you have different yield strength in different direction, that is plastic anisotropy, and the other one is elastic. Okay. So this is going to be isotropic. So it will look like this. Okay. And then kinematic is going to be like this. So the distance between the yield point of tension and compression is going to be same. So this distance is going to be same. Okay. But reality can be modeled in a much better way if you combine both isotropic model and kinematic model. So you have a combined model. In that case, you can have, you will be taking care of Bauschinger effect also, and you will be taking care of the good things which are there in isotropic model. What is the good thing? That this expands. Okay. So this is how the isotropic model will look like, this circle. This is how the isotropic model will look like when you plot it in biaxial condition. Okay, so you have sigma 1, sigma 2, there is no strain here. Okay, so in sigma 1 direction if you go, that yield strength is increasing. Okay, and also in sigma 2 direction it is increasing. So if you follow Tresca criteria for a biaxial condition, then it will be sigma 1 minus sigma 2 by 2, the maximum shear stress. Okay, and if that crosses a critical value, then you can define your yielding. So that will be following 45 degrees from there between sigma 1 and sigma 2. Okay. So kinematic hardening will look like this, the red circle, because the radius of the circle is not going to change, but the origin is going to shift. Because for each yielding, you are defining a new yield point. Okay? In the first case, the first yielding happens here, and then the next yielding happens here, and so on. Okay? When you reverse this direction, then yielding will be happening a little bit before that, but the distance is going to be 2 into this. So that is going to be constant, and this will be constant for this case also. So that will be equal to what was the difference here. Okay, so it will always be the circle of the same radius, right? But so if you look at that that diagram which was in the previous slide, this one for kinematic. Okay. So in this case, for the first cycle, if you shift the origin, then it will look like isotropic hardening for the first yielding. Do you follow what I am saying? No? So, the specific. And you are going to have yielding a little earlier, right? So you go here, and then you go there, and then you come back, and then you go here. Okay? I will have to create a larger distance. Okay. And then this will go, no, this will be constant. So this will join this one line. Right? So for this case, if suppose I start from this point, which is 2 sigma naught by 2, then it looks like an isotropic hardening because the increment is same on both. So what is the difference in kinematic hardening? Sigma naught is higher in tension side or in one side, and it is lower in other side. So I can always find a midpoint, right? And if I shift my origin to that midpoint, then it looks like isotropic, isn't it? If I shift my origin to the middle point, then I will have same distance in the tension, same distance in the compression. It will look like isotropic. Okay? So that would mean that kinematic hardening is isotropic hardening with an origin shift. And each time for isotropic hardening, the circle will have increasing radius. That will not be the case with kinematic, because that radius is constant, which is 2 sigma naught by 2. So sigma naught is the radius for kinematic hardening. Is it okay? So this is how kinematic hardening will move in every increment of yield strength. Okay? And the yielding, maybe I have discussed this in MM302. So this cylindrical surface is the locus of von Mises criteria. Okay. So von Mises criteria was sigma 1 minus sigma 2 whole square and sigma 2 minus sigma 3, sigma 3 minus sigma 1. Okay. And if I imagine it to be a uniaxial condition, so in that case sigma 2 and sigma 3 will be 0 and sigma 1 will be equal to sigma naught when it yields. Okay. So whatever is the condition, it should always yield at yield strength. Okay, even if it is not uniaxial. So I can put this combination equal to 2 into sigma naught whole square. Right, because if I put sigma 2 sigma 3 equals to 0, then what it becomes is 2 sigma 1 square is equal to 2 sigma naught square, so sigma 1 is equal to sigma naught. So from that I can write this. Okay, so this looks like a cylinder when you plot it along three axes, three principal stresses, sigma 1, sigma 2, sigma 3, and the axis of this cylinder will be along the mean stress, sigma 1 plus sigma 2 plus sigma 3. So 3 times of that is hydrostatic stress. Okay, so von Mises criteria has no effect of hydrostatic stress. That's why you see that this cylinder is not changing. If I move along this axis wherever, so here my hydrostatic stress condition is 0. I have no hydrostatic tensile or compressive stress. When I go on the positive side, I have hydrostatic tensile stress. So there will be a volumetric strain in the positive direction, so things will expand in all directions. Okay. In that case, I will have no change on yielding curve. Okay. If I go in the negative side where I have a hydrostatic pressure, even then I will have no change on the surface of the cylinder. For any state of stress which remains inside this cylinder will be deforming elastically. And all those points for which the von Mises is equal to sigma naught will lie on the surface, because that's the equation of this surface. So all of them will be deforming plastically. And when you go to next yield point, this cylinder will change its radius. Okay. Well, these are some equations which you should be knowing. Okay. So this also we have explained. Well, so the step here is you find out if there is any uniaxial strain, if there is any shear, and if there is any hydrostatic component. Okay. And hydrostatic component, as I said, will not be affecting anything. So these are the equations which you should know. So I'm just running the presentation. So this I have explained, no? This part. So for the case of shear, so this is uniaxial condition, right? And if you have pure shear, then you will have values here and none there. If you have just shearing, no tension, in that case you will have tau xy, tau yx, and there will be no normal stresses. Okay? So in that case, this equation will look like minus alpha alpha. Well, no, strain, not stress will look like that. So stresses you will have here something, and these will be 0. So how do we proceed in algorithm is we take a trial value and check whether the von Mises has crossed the yield point or not. If it has not crossed the yield point, then everything is elastic. Then we follow that elastic modulus versus Poisson's ratio relationship, and we calculate strain and stress, and we write it down in the output file. Then go for the next increment. There is no convergence in elasticity. There is no iteration. Okay, nothing is there, straightforward. Then once it will cross the green line, then you will have that non-linear algorithm where you will have a trial stress. Okay, and if it is ideal plastic, then you must return to this value. Okay, so initial point from here, you will take a tangent. Okay, and then you will reach there. Then you will calculate the error. You will have this much error. Do you follow? Okay, and then you will try to come back to the yield point which you know. Okay, yield point is an information given to the model, otherwise you cannot model. Model cannot predict yielding. Okay, so in every increment of strain, you will be trying and coming back, trying and coming back, trying and coming back, and this is how you will model ideal plastic situation. Okay, and this is the case of shear. Okay, so you only have shear strain, there is no hydrostatic strain, and then you calculate the stresses, so you have 2G here. Okay, so in that case where you had uniaxial condition, the slope was E, elastic modulus. In this case the slope is 2G. Okay, so you see that hydrostatic component is 0, so there is no pressure, and there is von Mises, which is 2 root 3 G into alpha, whatever is the value of alpha. Okay, so on alpha versus von Mises, in this case you cannot plot P here, which was the case in the previous condition. So our x-axis was hydrostatic stress. We don't have hydrostatic stress. Here we have hydrostatic, so it will not look at all, so you can't see anything. It will always be on this axis. If you plot against alpha, then it will be increasing as alpha increases. Alpha is the strain, so as much you deform, the stress will increase. Stress in this case will not increase because this is ideal plastic. Okay. So you see trial stress you cannot see on PQ plot, but you will be able to see that on the other plot. Okay. So this is another case of uniaxial loading. Okay. You have only sigma 1 1, which is E alpha. So in this case you have hydrostatic stress because you have normal stress, which is alpha by 3, isn't it? E alpha by 3. Okay. Vipin? समझ में आ रहा है ना? नहीं आ रहा है. Uniaxial condition. So you are applying, you have a tensile sample and then you are pulling it. So you have a principal stress sigma 1 1, which is sigma y by. Okay. And then you have no stresses in other direction. Okay. So none are there. So because of that, you will have a hydrostatic stress component and you will have von Mises component. Okay. So von Mises will be defining the yielding. Hydrostatic will have no influence on it. Okay. So again, if you see PQ plot, then you take trial, it is an elastic, do the calculation, move ahead, it crosses yielding, then you have to converge and keep on doing the same thing. Okay, so this is okay, this is also okay. So in this case, when you have plasticity, I have explained this part also. How do you calculate EP, which was H? Okay, if you remember in the last class, you have a different slope in plasticity. Do you remember? 1 by E. So 1 by Et is equal to 1 by E plus 1 by EP. So Et is equal to E into EP by E plus EP. Do you remember that?
Yes, sir. Yes, sir.
So that is that, and this is okay. This is, shouldn't worry about that. So if you have to write in the equation form, ideal plasticity looks like this. F of sigma ij is von Mises. If you are taking von Mises criteria, that function is, you know what F is. Okay? If you are following Tresca criteria, then you will have a different function. You can follow some other criteria also for yielding. In case of isotropic, whatever is your yield function, these are called yield functions. Okay, the yield function minus the current value of yield strength must be 0, so that you have to converge. Okay, you do non-linear iterations so that the difference becomes equal to the tolerance value. Okay, in kinematic hardening, you have a stress which is subtracted from the yield strength when you reverse the direction. That is called back stress. So when you load in tension, then you go back in compression. So in compression, the sigma y naught will be subtracted by a value, so that the difference between sigma naught in tension, sigma naught in compression is constant. That you have to maintain. So this subtraction is called back stress. This simulates the Bouchinger effect. Okay. So in kinematic hardening, you instead of converging this, you converge this equation, and in combination, you will have something like this. So this part will not be changing in kinematic hardening. This will always be constant. But in combined plasticity, where you take isotropic and kinematic, you will have a function. So yield strength will be a function of plastic strain that will keep on increasing, and you will have to converge this. Okay? And then those are the equations which, so this part I have explained, no? So strain can be broken into elastic part, plastic part, then you have plastic slope of the curve. Okay, so plastic modulus, which is EP, and this is what we did in the last class. This is what we derived. So now we know in very, I'm not going to explain the calculation in too detail because it's a 2 credit course. So let us say that we know now that how to calculate elastic deformation, then plastic deformation. And what is the next thing now? After plasticity, what do we do?
Break it. Fracture.
और फ्रैक्चर के पहले क्या होगा? चैप्टर का नाम नहीं पूछ रहा हूँ मैं. क्रैक प्रोपगेशन तो फ्रैक्चर हो गया. इनिशिएशन, हाँ, उसके पहले क्या होगा? क्या? हार्डनिंग तो प्लास्टिसिटी में हो गया. Why necking happens? तुम सो रहे थे फिर भी जवाब दे रहे हो. Continuous Dr. Prince and then me, it is too much. Should have some gap.
Yes, yes.
Isn't it? Yes. Then attendance is not mandatory. Why did you come? मैं बहुत ज़्यादा अच्छा पढ़ा रहा हूँ क्या? So before fracture or crack initiation, you will have damage in the material. Okay? So we'll not discuss mathematics now. Let us just talk about what happened. And in the lab, we will do experiments which we have done in our MM304 lab. Tension किया है, compression किया है, bending किया है. So we'll try to do that. Maybe the whole syllabus will be finished by only modeling tension condition, but if we can do more, then we'll do more. Okay. So plasticity we have simulated. Now what is the next thing? Damage. Before fracture, damage will initiate. Okay. So in our stress strain curve, if this is the stress strain curve, if you unload here, it will follow this slope. But if you unload there, the slope will change. Okay? The slope will keep on decreasing. Because the material, if it is a ductile material, then in ductile material, you have created some voids, and those voids are decreasing the load bearing capacity of the material. Right? So that's why the stiffness is the representation of load bearing capacity. To the amount of strain, how much force or stress a material can show as resistance. Or vice versa, if you apply a force, how much resistance can be shown in the form of deformation, or how much deformation a material can take. Okay, so as you increase the stress or strain, so deformation in the material initially becomes stronger and tries to resist the deformation you are giving. Okay, but after a while it is not able to not only resist the deformation, but it takes more deformation. It becomes softer. Okay, and it becomes softer because there are disease inside, there are sickness, virus and bacteria in the form of voids in the material, and it has become sick, it has become damaged, and slowly it will die. So it will break into two parts. So how do we simulate damage? How can we simulate damage? So how much time do we have? Oh, we have 8 minutes. So if this is a small piece, very, very small piece of the tensile sample, which I am testing, and some voids have been created. They have nucleated and they have grown in the sample. Okay? So when the voids were not there, whatever force I applied, so the applied stress was force divided by area. क्या चाहिए? कुछ नहीं चाहिए. So this is force divided by area, right? Once I have created these voids, and now just look on this plane where I have dissected it, the real area has decreased, right? Because these voids, they have no surface, so that area is gone. Okay, so I have different area now. Okay, so my new stress will be higher or lower? It will be higher. So I will have same amount of force divided by a new area, and this area has decreased, so I have more force. Now you can imagine why necking happens, because locally the stresses are increasing. Wherever the damage has initiated, the stresses has become higher and more deformation will take place there. Okay, so can I define this in terms of that? If my new area A dash can be defined as a function of old area with a damage parameter. So omega defines how much damage is there in terms of area fraction. Okay, so if there is no damage, then this is equal to that. If damage increases, then this is smaller than this. Okay, so I can define sigma 1 is equal to F by A into 1 minus omega, which is sigma divided by 1 minus omega. So in every step of finite element calculation, I have to change a little bit and everything else will remain same. My elastic calculation from the displacement solving Ku is equal to F, all those things will remain same. From displacement I will calculate strain by using B into U transpose. From that I can calculate stress, dBq. This stress I need to update with omega if there is damage. Okay, so for this I need to define certain points. I need to define when omega will become greater than 0. That will be the initiation point of damage. Okay, and you also can see that let us say that I have some slope between stress and strain, some slope E total. Okay, so when my stress has changed to this, sigma divided by 1 minus omega is equal to Et into epsilon, then I can write E into 1 minus omega into epsilon. So I can also say that my stiffness is decreasing, and it is decreasing, isn't it? So this is called stiffness degradation for obvious reasons. Okay, so I will have to define a point where omega becomes greater than 0. And now also look at this small volume. That voids have been created and stresses are increasing, and these voids will grow, and more volume will become empty. It will become more and more porous. Okay? And when will it fail? When will you define the failure of this small piece? When the whole thing becomes vacant.
होल आपस में मिलने लगेंगे वो होल है ना आपस में
हाँ, coalesce कर गया, ठीक है. So porosity is increasing. So omega is increasing. Okay. So when will you call that failure has happened, or the element will not be able to take any load? When the omega becomes 1, then it starts from 0. But when it becomes 1, that means it is empty. So no material can go to that point कि अंदर हवाई है, बाहर फिल्म है, तब तक नहीं टूटेंगे, ऐसा तो नहीं होता. Okay? 70% वैक्यूम हो गया, टूट जाएगा. 80%, 90%, 95%, it will fail. Okay, so we'll have to define a failure criteria. So when omega becomes equal to omega f, then you stop calculating in that element, define that element is gone from your global stiffness matrix. It's done. Don't take it in calculation. And do the calculation, keep on doing the calculation in other elements. And all those elements which will be reaching this criteria will be removed from your simulation, from your calculation, and then you can simulate a tensile sample really breaking in your computer code. Right? So that's all. We'll end today here.